How you guys doing? Welcome to Chemistry for Anatomy and Physiology 1. We'll try to keep this thing as short and sweet and right to the point as much as possible, and I'll try to be as animated as possible. Of course, it's always hard when you're lecturing, talking to a screen, but I'll try to be as exciting as possible. So, let's get into it. Right off the bat, it's important to remember you only have to worry about the slides with the green check marks at the bottom right. So focus on those because those are the ones that I'll be expecting you to know. So that's that. We'll start with a little bit of terminology. What is matter? What is elements? What is an atom? Protons, neutrons, that kind of thing. Atomic mass, atomic number. So what is the difference between, say, an element and an atom? Well, an element can be made out of a whole bunch of atoms. It just has to be the same atom. An element is a substance that can't be broken down to other substances by chemical reactions. So say you're holding a block of gold. You're holding the element gold, but it contains a whole bunch of gold atoms. An atom is one single unit of the element. That's the difference between atom and element. Moving on, life. All kinds of organisms. All organisms have roughly the same amount of. We're composed of, as far as ratios, the same amount. We all have roughly 96% of carbon and hydrogen and oxygen and nitrogen. Roughly 96% of all organisms are composed of about that much, and the remaining 3-4% are the trace elements like potassium and sulfur and calcium and so on. And you can see that in this table here. Here are the 4: oxygen, carbon, hydrogen, and nitrogen. And so that's why we always we focus a lot in on these ones, just because we're made mostly of these 4 atoms. And however, you got a whole bunch more, but add them all up, and they only comprise the of 3.7%. So so that's what those two slides are trying to get at. Atoms can be further broken down into subatomic units called protons, neutrons, and electrons. And you'll always find them in the same places in an atom. So let's say, for example, we're looking at oxygen. I know that oxygen has 8, and we'll show you this later on a periodic table, but I know that oxygen has 8 protons. I know that oxygen has 8 protons. When you look at a periodic table, and we'll show you this in just a second, it'll have a number 8 up on top. It'll also have on the bottom a number, a lot of time, depending on how detailed the periodic table is, it'll have another number on the bottom. The number on the top always tells you the number of protons that particular atom has. So because I have this memorized, and I'm never expecting you to memorize any of the numbers of any of the atoms. It's just I expect you to know what the number means. What does this number mean? What does the number on the bottom mean? The number on the top is the number of protons that atom has. It's called the atomic number. It's the atomic number. However, the atomic mass, which is on the bottom, is how much mass it has, the total amount of mass. It's not just the protons, because an atom, it consists of protons and neutrons and electrons. That's the atomic mass on the bottom. Let's just take a look at, let's draw out oxygen. So if you got some paper, let's just go through it. I know that oxygen has, so here we have oxygen here. I know that oxygen has 8 protons. Protons have a positive charge. So let's just draw in, just to grab some scratch paper, notebook paper, and let's just draw in the nucleus 8 protons, depicted by plus signs. So we got 1, 2, 3, 4, 5, 6, 7, and 8. There we got 8 protons. We're starting to form the nucleus now, okay? We're starting to form the nucleus. We also got neutrons. Neutrons have no electrical charge. Let's just put dots. Let's just depict these with dots. How many, though? Well, I already know. If whatever atom, whatever number of protons it has, generally speaking, it has the same exact number of neutrons. So 1, 2, 3, 4, 5, 6, 7, and 8. Now we have completed the number. We've completed what you're ever going to find in the nucleus. We're looking at the nucleus here. 8 protons, 1, 2, 3, 4, 5, and 8 electrons. So far, so good, guys. So, why are we dealing with the number 8? Well, because oxygen has a big fat 8 on the top of its on its sign. 8 always refers to the number of protons, and since there's 8 protons, we know that there's 8 neutrons, and since there's 8 neutrons, we know how many electrons it has. Now, you guys already should know about the orbital shells, and you should know how many electrons fit in each orbital shell. You should already know this, probably even from high school. So let's just change colors here. The first orbital shell, how many electrons can the first orbital shell hold? Up to, the number is up to 2. It goes 2, then it goes 8, 8, 8, 8, all the way up, just like that. Well, we have a total of 8 electrons. So the first one holds 2. So let's just keep counting. So there's 2 things you got to think of, is how many electrons total and how many are on each orbital shell. So we got 1, 2, we got 3, 4, 5, 6, 7, and 8. Does our picture look good? Does the first one only hold, first of all, do we have a total of 8 electrons? Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8. Yes. Now you say, okay, well, is each one, do I have the correct number in each one? Well, I got 2 on the first one. That's good. And I have more, so that means, and remember, you can't, don't put just 1 in the first orbital shell if you're going to have more after that. So if you have more than 2, you got to draw an outer shell, another shell, and the first one has to be all filled up. It should be anyway. That's just how we draw it. Electrons do jump back and forth, but this is how we draw it when it's in its lowest state of energy. 1, 2, and so therefore we have 6 on the outside. Did we draw too many on the outside? Well, how many does the second one hold? It holds up to 8. Well, I only got 6. Okay, so now we are complete. This is a perfect depiction of all the subatomic particles in an oxygen atom. Okay. 8 protons, 8 neutrons, 8 electrons. Where do the electrons exist? Not in the nucleus. They exist in the orbital shells. Where do the protons exist? They exist in the nucleus. Where do the neutrons exist? They exist in the nucleus as well. Try not to talk too fast, but also I don't want to just drag it on and don't want you guys to be bored. Okay, so far, do you understand what you need to know so far? There's another thing, which is what kind of electrical charge do each of those 3 subatomic particles have? Protons have positive charge, Electrons have negative charge. Neutrons have no charge. Okay. So far, so good. Now oxygen is complete. We can continue to talk about what these numbers are. If this is the atomic number, this is what we call the atomic mass. The mass is the weight, the mass of the entire thing. Well, we got 8, and just add them up. 1, 2, 3, 4, 5, 6, 7, 8. Keep going. 9, 10, 11, 12, 13, 14, 15, 16. So if this is 8, why is it 16 if you still have the electrons? Well, yes, add up the electrons. However, electrons have a very little mass. They weigh almost nothing. So if you look at the periodic table, you'll find that this is like 15.99999 actually. Roughly 16. We're anatomists. This is biology. We're not going to get to delve too much into the chemistry. This is just the basics, and this is totally good for us. All right. Let's move forward here. So we're done with this slide. Let's go to the next one. That cloud that we're seeing here, that's again referring to the orbital shells. The first one, the second one, the third one, and so on. All right, here's another example. Here we got a nucleus and we have orbital shell. This particular nucleus has how many protons? It has 2. So since it has 2 protons, it has to have 2 what? It has to have 2 neutrons. Where are all those guys? Those are all in the nucleus, and therefore, since there's 2 and 2, there has to be 2 electrons. Why is there only one orbital shell? Well, because it only needs one orbital shell. Because the first orbital shell can hold up to 2 electrons. All right, so that's that. That explains. If you can walk through that, that's all that I'll ever expect you to know. Here are those few words that we were just talking about: the atomic number and the atomic mass. What's the atomic number? It's the number of protons. What's the atomic mass? It's the total. It's the protons and the neutrons and the electrons. It's all of them. What's an isotope? Well, if we go back to our oxygen example. What's this 8? We're just going to drill it into your head. What is the 8? What does it represent? The number of? Go ahead, shout out loud even though I can't hear you. It's the number of protons. That number, if that number changes, you change the element altogether, which doesn't usually happen. At least for our, in humans, it doesn't happen. Yeah, sure, it changes on the sun, but it doesn't happen in humans. You can give electrons, you can take electrons, you can share electrons, you can even take away or add neutrons. But if you change the number of protons, you change the element altogether. You change the atom. So we typically don't talk about changing the atom. If it's a number 7 or a number 8, it is no longer oxygen. What is an isotope? An isotope, so how many neutrons does oxygen have? It also has 8. It has 8 neutrons. However, an isotope of oxygen would be like 7. So you didn't change the number of protons, but now you just have one less neutron. And that's still considered oxygen because the number of protons never changed. All right. I hope you guys got that. If you need to absorb that, just hit pause or whatever, jot it down, or highlight it in your own slides or whatever. That's the good thing with, online videos is you can pause it as much as you need or whatever, or review, rewind or whatever. Okay. No check mark. No check mark. No check mark. Now we're going to start. Yeah, this we've already covered. We're just talking about orbital shells, so we can skip this one. This slide, just really quickly, here's the orbital shells that we're talking about. Now, what is this? What are these arrows? Well, you take a hot pocket and you stick it in the microwave. You're adding energy. You're heating it up. You're adding energy. So whatever electrons were here and here and here, they're going to jump. The electrons can jump to higher and higher orbital shells because that's how they. When you add energy, they get more excited. They get more excited. They need more space. They need more space. They move away from the nucleus, and this is what these arrows are showing. They get more excited, so therefore they actually can jump orbital shells. Now, on the other side of the coin, you have something that's hot, and the whatever element, and then it starts to cool. Those electrons will jump back down to their lower state of energy because they're losing energy, and that's how they lose energy, is by coming back down, closer and closer back down to the nucleus, not without changing the element or anything like that. That's all that this slide is showing. As long as you just kind of understand the general idea, we're good. I'm happy. All right, skip. All right, here is a periodic table, and let's look at lithium. Now it's time to test our knowledge, okay, guys? You tell me, what is that 3 and what's that 6? It's small, so I kind of had to look closely. What is that 3 there? What is it? Go ahead, tell me. What is that number? What's the title, and does it mean, and all that stuff? The 3 is the atomic number. The atomic number is what? It's the number of. Go ahead, say it, guys. It's the number of protons. If you change the number of protons, if you add one, you no longer have lithium. You have beryllium. If you add one more, you no longer have beryllium. You now have 5. That's boron, or carbon, or nitrogen, and you just keep adding and adding. What is that number? What is the number on the bottom? It's the total number of subatomic particles, which is all the protons, all the neutrons, all the electrons. So it's generally double. You have, if carbon is 6. If the atomic number is 6, the atomic mass is 12. In general, why? So wouldn't you triple it? No, because you just double it, because it's just the protons and the neutrons that have the mass. Electrons have very little mass. Okay. You guys get all that? As long as we're here, let's just briefly just talk about what these 2 arrows here are. You got 2 arrows moving. Let's see here. Go like this. You got these 2 arrows that are moving, that are pointing to the top right of the periodic table, and that is talking about the electronegativity. The closer you are over here to the top right, the more electronegative the atom is, and the further down and to the left you are, the less electronegative the atom is, and we'll talk about that in just a second. Or you know what, that might even just be good enough. Okay, before we get off this slide, is there anything else that we need to know? That's about it. I'll just want to say this one more time. I never expect you to memorize any atom, any element, any number. I don't know. I don't care that you remember where they are, anything like that. I just want you to understand what the numbers mean. So if I were to give you nickel, for example, and give you some numbers, I'd expect you to understand what they mean, but I wouldn't expect you to produce the atomic number and the atomic mass. Okay, guys? All right, all clear? Okay, this particular slide is just showing how all these blue atoms are metals and how the brown are nonmetals. You got potassium, you got calcium, you got magnesium, you got sodium, lithium, beryllium. These guys, iron, cobalt, nickel, copper, zinc, these are metals. Okay? The ones over here, you got carbon and nitrogen and oxygen and sulfur, and these are nonmetals. Generally speaking, when you put, well, maybe I don't want to get ahead of ourselves, but we are about ready to move into different kinds of bonds. I'm going to ask you for just 4 bonds, 4 different kinds of bonds. There's actually 5 or 6, I think. I'll only ask you for 4. The 3 main bonds are covalent, ionic, hydrogen. Covalent, ionic, and hydrogen. Now, the covalent can be further subdivided into polar and nonpolar covalent. We'll get into that. But as long as we're on this slide, I just want to tell you, I want you to remember that generally speaking, a non-metal bound to a metal typically is created by an ionic bond, a non-metal and metal. For example, sodium chloride, metal and non-metal, calcium chloride, that kind of thing. However, what is water made out of? Well, water, let's see here. Water was, what was it, you guys? Water is H2O. So you got H over here. Well, this is brown. And you got H2O. You have 2 of these and you got 1 of these. Well, both of these are brown. These are both nonmetals. So that's probably not an ionic kind of bond. Okay. I like this. This is a much simpler periodic table, but because there's not as many things, but it is depicting the electrons. And what do you notice? What do you notice about every single one of these? Well, I noticed that they all have more than 2 electrons, and therefore the first orbital shell is completely full, and the first orbital shell holds only up to 2. So this guy has 2, this guy has 2, and this guy has 2, and this guy has 2. The second shell holds up to how many? It holds up to 8. This only has 1 extra. This has 2. This one has 3 on the outside. This one has 4 on the outside. This one has 5 on the outside, and so on. But as soon as you get more than 8, you have to add an orbital shell. That's because this one has 2, and then it has another 8, and then it has 1 extra. So sodium has... Now you, at this point, you should be able to tell me all kinds of stuff. What is that number 11? What's the label? What's the fancy word? That number 11, sodium on the top, up here. What is sodium? I'll just pause. Sodium, the number 11, is the atomic number because sodium has 11 protons and 11 neutrons and 11 electrons, just pounding it in your head over and over and over. Sometimes that repetition is very helpful. So, since it has 11 electrons, we know how to draw them out. We know how many orbital shells because the first one only holds 2 and the second one only holds 8, so that's 10. And so if there's 11 electrons, well, then it's going to have this outermost shell will only have 1. By the way, as long as we're here, let's just talk about valence electrons. Valence refers to the outermost shell. Valence electrons. So let me ask you, when we look at lithium, how many valent, and you don't even actually need these drawings. You should be able to draw them out on your own, as long as I give you one piece of information. But since this is already drawn out, all that you should be able to answer it quicker. How many valence electrons does lithium have? Test question. Answer is, how many valence electrons? How many electrons are on the outermost shell? Only? It's not 3. The answer is 1. Go to oxygen. How many valence electrons? Not electrons, but valence. The answer is 1, 2, 3, 4, 5, 6. The answer is 6 valence electrons. How many electrons in total? Well, you got 6 plus those 2. That's 8. All right. Now we have valence electrons all taken care of. Why is that important? Because it's the valence electrons that will be shared or given away or taken, that kind of thing. All right. So, and this is checked, and we already know all this. We already know this, you guys. We know all this stuff. Here's the atomic number. Here's the atomic mass. Atomic number, mass is usually double the atomic number. This is the number of protons. The number of protons can never change. Otherwise, you change the atom into something completely different. Why isn't it tripled? Well, because electrons don't weigh very much, so you basically would just double, even though this number represents all the atoms, all the protons and neutrons and electrons. Okay. Here's the electron distribution diagram. It's just one orbital shell. Why only 1? Because you only have a total of 2 electrons. What's this gray thing in here? That's the nucleus. Okay. Easy peasy. Let's keep going. Click, click, click. These are just kind of zoomed in. We can just click forward. Valence electrons. You tell me, what are valence electrons? You should already know. Outermost electrons. Orbital shells, we're good to go. Now we can zoom in even more as far as the 1s, 2s, 2p orbitals. We won't even get into that, even though that still should be fresh in your head, but we won't get that detailed. So that's why. Okay. Now it's time to talk about the chemical bonds. First of all, we have covalent bonds. All you got to do, look, you're never going to remember what is what unless you just break down the word. Just break it down. You know what covalent electrons are. Valence electrons are the electrons in the outermost shell. So if these were 2 orbital shells, and I have this diagram here, and I asked you how many valence electrons, you would say there's only 3. What does co mean? Oh, I heard that before. You got cohabitation, cohort, co-ed. It's sharing. This covalent means sharing. The electrons are shared. Okay? The electrons are shared between 2 different atoms. I need them and you need them both So if we come together, I'll use yours and you use mine, but just the covalent ones, just the ones in the outermost shell, not all of them. Let's take a look. Hydrogen. Hydrogen has one proton and one electron. Is hydrogen happy by itself? No, it's not. Because remember, the first orbital shell holds up to 2. If it had 2, it'd be happy. Because 2 is complete. It is not happy by itself. It doesn't even exist in nature, you guys. Hydrogen by itself doesn't exist. It's hydrogen is a in nature is a what we call a diatomic molecule. 2. There's always 2 bound together. So what's happening then? What are we looking at here? Well, this hydrogen has one electron. And it's not happy. And this hydrogen on the left has one electron. Well, if they both shared an electron, this guy here now has 2. And now this guy is happy, is so long as he's next to this guy. And the guy on the right is happy. He now has 2, as long as he's sticking to this guy. This guy now has 2. This guy has now 2. It is a win-win situation. Okay? That's covalent. They are both sharing. They're both happy. Now, nuclei pull on electrons, just like the Earth is pulling on the moon, because the Earth has mass. The Earth is pulling on everything on top of the Earth because it all has mass. The moon is pulling on the Earth, actually, because the moon has mass. The moon has gravity. They're pulling on each other. In the same way, this proton in this hydrogen molecule is pulling on these guys, and this guy is pulling. They have mass. It's the same thing. It's gravity. It's the same exact thing. It's the exact same it's the same exact reasoning. It's the same physics. And since this hydrogen has the same number of protons as this hydrogen here, they're pulling equally. And because they're equally, this is what we would call a non-polar covalent bond. Non-polar. Now, yeah, okay, I'm just kind of getting ahead of myself. That's okay. We'll get back to that for a second. If I drew out an oxygen here and another oxygen here, and I drew something like this, or if I drew, say, a carbon and a hydrogen, and I drew something like this. This guy right here is sharing 2 electrons. Or actually, let's just go back to our hydrogen example. 2 hydrogens sharing looks like this, right? Well, we generally would draw it like this. Hydrogen, line, hydrogen. In other words, that one line, that single bond, is depicting the sharing of 2 dots, 2 electrons. This is sharing 2 electrons. This is sharing 2. This is sharing 2. Here over here, these 2 oxygens are actually sharing 4 because you got 2 lines. Each line is 2. 2 plus 2 is 4. All right? Okay. So that's that. This whole slide you already know. This is just saying the same thing. Let's look at these 2 hydrogens. We already know this example. That hydrogen was not happy. This hydrogen, I'll get the laser pointer. This one is not happy. This one's not happy. Why is it not happy? I mean, by itself, because it only has one hydrogen. It wants a complete orbital shell, and this one wants a complete orbital shell, and therefore, if they came together, they can both each share their own, and now this guy has two, this guy has two. It's a win-win. Oxygen. If you remember, we said oxygen has 8. Has 8, an atomic number of 8, and so if it has 8, that means, how many electrons? 1, 2, 3, 4, 5, 6, 7, 8. All good? No, it's not good, because the outermost shell is not happy. The outermost shell wants to have, remember, it goes 2, 8, 8, 8. The outermost shell wants to have 8. How many do we have? How many valence electrons does oxygen have by itself? It has 1, 2, get the laser pointer out. It has 1, 2, just count them up. 3, 4, 5, 6. This oxygen only has 6, and this oxygen only has 6. Both oxygens are not happy. That they don't even exist in nature, you guys, like that. They don't exist in nature like that. They always come together, unless you talk about the ozone, like O3 or whatever. But here down close to the Earth, they're a diatomic molecule, O2, 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 just like H2. You know what happens if they're not happy? What do you think happens? They're called free radicals. They're not happy, and so what are they? They're very irritable. They're unstable, and because they're unstable, inside of our which we do, we breathe in free radicals, and we consume them in our food, and so they get into our DNA, they get into our cells, into our DNA, and because they're very jittery and unhappy, what do? They end up tearing up our DNA, increase the risk of mutations and cancer and all this stuff, and so what do you do to combat free radicals? What do you eat? You consume vitamins C and vitamins E, blueberries, whatever. Those, what are they called? They're called antioxidants. What are vitamins? What are, like, all those superfoods or whatever? They just contain a bunch of vitamin E and vitamin C. So what? Well, so what of vitamin? I don't get it. Well, those particular vitamins can easily give away electrons. Here, oxygen. Just take 2, or can receive electrons from free radicals. So they can easily give and take electrons, which makes free radicals like oxygen by itself, the lone wolf oxygen, happy and not so dang unstable. It makes it more stable, and so the oxygen is now happy, and it doesn't wreak havoc in your DNA. That's what free radicals, antioxidants, and vitamins. That's how those are all related to this exact thing that we're talking about. Some real life stuff. Like the only disadvantage of like running, like exercise, is that we breathe in more air. You breathe in more air, well, you risk breathing in more free radicals. But I mean, we consume way more. I mean, we consume way more. All you got to do is just eat healthy, and I mean, there's way more advantages. There's way more pros than cons with exercising. I mean, I can only think of one con of like going out for jogs, which is just, that's the only one, is breathing in more free radicals. There's unlimited stuff. I mean, just study after study. I mean, this is It's very, very well documented stuff. Advantages to exercise, even cognitive. You guys, you can be smarter just being you actually become smarter just by running or whatever. I always use running as the example, but like even yoga or whatever. Even though I don't really consider yoga, it's exercise. It looks funny. That's all. I love yoga. All right, I love yoga. All right. Okay, I just realized I don't even need to have headphones on. All right. Oxygen. Take a look at oxygen here. Again, oxygen, 8, it's not happy. It wants 2 more. It can get 2 from 2 hydrogens. And these guys are not happy. Now, let's look here. What kind of covalent bond are we talking here? Or are we talking about? This guy is pulling on these electrons as much as this guy. The protons in here are pulling equally on these electrons towards the center as these guys are pulling on these, as the protons over here are pulling left and right. Therefore, this is what you would call, this example here is non-polar covalent. Non-polar. We hear that all the time, right? The country is very polar. The country is very polar because you got blue and you got red, or you got Democrats and you have 2 ends that are very, very different. But in this example, this is an example of non-polar because these ends are the same. They're pulling equally. However, take a look at water. It's not the same. Now, if this hydrogen was way over on this side, and this would make like 180 degrees here, this would be flat, then it would be actually nonpolar, but it just doesn't behave like that. Hydrogen ends up coming close to this hydrogen, and so the atoms, the protons in this oxygen, there's a lot more, aren't there, than the protons here. So this guy is pulling the electrons closer to its nucleus than these guys can. And if it's pulling the electrons, then it becomes more negative. And so this end becomes partially negative, and these guys become partially positive. Why are these positive on this side? Because the electrons are closer to the oxygen's nucleus. This is what it looks like, you guys. Partially negative and partially positive. And because that's true, you have what we call polar covalent. Water is an example. Water is a polar molecule. This is an example. I love my handwriting. I'm writing with my right hand, even though I'm left-handed. This is an example of polar. This is an example of nonpolar. Okay. I love my O's and A's. They're all like squashed. There we go. All right. Nonpolar, polar. You guys get it? Methane, because these angles between the oxygen and the hydrogens, the carbon and hydrogens are all the same. This ends up being nonpolar. So this is nonpolar, polar, nonpolar, nonpolar. Okay? All clear? And if you need to review that, just pause or just rewind. Okay. I just kind of stuck these periodic tables in here periodically. No pun intended. Actually, pun intended. Anything we wanted to say about about this. Here are these two again. Tell me, is this diatomic molecule polar covalent or nonpolar covalent? Answer is nonpolar. Nonpolar. Polar. That's your test questions, by the way. Nonpolar. Electronegativity. We talked about the unequal sharing. Here, this is exactly, see, oxygen is partially negative on this side, partially positive on this side, and because it bends and that kind of thing. And because this guy is pulling on the electrons so much more, because it's just larger, because it has more protons in the middle, you can pull electrons closer, which makes this more negative, because electrons are negative. All right, so it's like the physics is easy. Like if you just get it, if you just understand that protons and electrons attract each other and that kind of thing. Okay, guys, we are actually more than halfway done, so we're doing good. Ionic bonds. Ionic bonds are different in that. Do you remember the hydrogen example? Hydrogen was not happy. It needed an electron, and the other one also needed an electron. They both need to share, but with sodium and chloride, this guy. Let me get my laser here. Sodium doesn't want it. It doesn't want that extra one. It would be happy in this orbital shell. The orbital shell, the second one would be totally full. And on the other side, chlorine would be happy. The chloride ion would be happy if it just gained one. So these guys attract each other. If one loses one and one gains one, it's not the same as sharing. They're not sharing. Because if they were sharing, then this sodium would keep its, and it would share another electron, and then that would not make this thing a full orbital shell. You see, it would have, these would be paired up, but then you'd just have two valence electrons just kind of floating there, and so this ends up being an example of an ionic bond. This is ionic. And again, you have one metal and one nonmetal, and that usually will help you remember ionic bonds. That it's help you to figure out that it's an ionic bond. It'll also help. In general, what is ionic bonding? It's one ion completely giving away an electron, and one ion completely taking an electron. No sharing. Okay. Good, guys. All right. I hope I haven't completely lost you. Here's just a quick little cheat sheet for you. Here are a bunch of metals and nonmetals. Lithium fluoride, lithium chloride, lithium bromide, and so these are all examples of ionic bonding between metals and nonmetals.
Sometimes atoms complete their outer shells by stealing or giving away electrons. This happens between sodium and chlorine atoms. An electron moves from the sodium atom to the chlorine atom. The outer shells of both atoms are now complete, containing 8 electrons. The chlorine atom now has 18 electrons, but only 17 protons. Because an electron has a negative charge, the chlorine atom now has a net negative charge. Such a charged atom or molecule is called an ion, in this case a negative ion. The sodium atom has lost an electron, leaving it with an extra proton, which has a positive charge. The sodium atom has become a positive ion. Ions with opposite charges are attracted to each other, forming an ionic bond. These ions combine to form a compound with new properties. In this case, sodium chloride, ordinary table salt, is formed.
A cation is a positively charged ion. An anion is a negatively charged ion. And when they come together, they're both happy. Ionic bonds make salts. Calcium chloride, sodium chloride, that kind of thing. Our streets in Minnesota are, they use calcium chloride. Super cheap in the wintertime. The fourth and final bond is called a hydrogen bond. It's the weakest. Remember that too. It's the weakest of all bonds. Now, you see this hydrogen here? And you see this oxygen? This bond? If you say this is a hydrogen bond, you are incorrect. We already covered this. This is a polar covalent bond. So where's the hydrogen bond then? The hydrogen bond you don't find within the molecule. You find it between two molecules. It's the weakest of all bonds. A hydrogen bond always has a hydrogen, and it just attracted to the larger atom on a different atom, to the larger atom on a different molecule altogether. So let's draw out water. So we got an O, H, and another H. Here's H2O. Well, there's supposed to be two H's there. Draw a little bond, little line. That's two electrons. Here's water. All right. Is that right there a hydrogen bond? Is that a hydrogen bond? No, it's not. That's a covalent bond. Matter of fact, it's polar. It's polar covalent. Now, we got another water here. Are any of these hydrogen bonds? Nope. So where's the bond? Where's the hydrogen bond then? The hydrogen bond consists of a hydrogen, but the attraction is between two different molecules. It's the weakest of all. So in this picture, just right here, in this diagram that I'm showing you, right here, you actually have two different kinds of bonds. You got polar covalent, and you have, hydrogen bonds. Now we are pretty sure we're all complete. We're all done with everything that I need to know, that we need to know about the four different kinds. Even though I'm sure you already took that. And it looks like we're going to start to skip a whole bunch. Yeah, we're looking pretty good, you guys. Just a couple more, just very, 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 very quickly. We'll continue this in a different chapter. Super easy, you guys. We got two terms that we need to remember. We got products and reactants. How do you know which ones are which? All you got to do is look at the arrow. Look at the arrow. The arrow is pointing to the right. This stuff is the final stuff. This stuff is called the products. That means the stuff on the back side of the arrow are the reactants. If the arrow was going the other way, then this stuff would be the products, and the stuff on this side would be the reactants. So whatever the arrow is pointing to are the products. Now, let's look at another example. Here we go. This arrow is pointing to the right. That means this stuff over here, products or reactants. Answer is, these are the products. What's the stuff on the left-hand side? Those are the reactants. Why? Well, because the arrow is pointing to the right. That's it. What is this? This is actually photosynthesis. You got a plant, and it breathes in carbon dioxide, and you got to give it water, and you got to put into the system some kind of energy. In this case, it's sunlight. And look, you can build something big. That's sugar right there, you guys. C6H12O6. That's a glucose molecule. And what else do you get? You get oxygen. Cool. So you got a plant can just take a waste, our waste, carbon dioxide. You just got to add a little bit of water to it, and you got to just put it next to the window, and it can make sugar. By the way, the sugar is not for us to eat; it's for itself to use. The plants don't make, they don't make glucose, for us to consume. We end up killing the poor plants, but they make it for them. They use the glucose for themselves, for their own survival, and they make oxygen. Their waste is our nutrition, oxygen. Okay, we're done. That's the whole thing, you guys. We are done. Thank you so much for we took about an hour lecture. It was kind of long, but we did get through it. So good work. Study up, review, refresh. You can watch this over and over if you really need. It's totally fine if you need to. It's totally okay. Go through those, pay attention to what I was asking and how, and you can do the same thing, and you can write these questions down. You can practice. Just keep making other examples, and so when you take your exam online, if you made good notes, that's your incentive to make good notes, is you can use them on the test. You just have them out, and you don't got to stress out, because remember, the big exams are timed. So there is a time limit once you actually click on it and open it up. All right. Thank you very much, everyone. Thank you for watching. Study up, enjoy, and hopefully we'll be able to make a few more here in the future. Alrighty.